Good afternoon. Welcome to lessons from 2 years of crypto audits. We're in the Jasmine room. This is Jean-Philippe Aumasson. A couple of brief notes for you. Stop by the business hall located in Mandalay Bay, Oceanside and Shoreline Ballrooms on level 2 during the day and for the welcome reception tonight at 5:30. The Black Hat Arsenal is in the business hall on level 2 as well. And also this evening, please join us for the Pony Awards in Lagoon JKL at 6:30 this evening. A couple of things just out of respect for your fellow attendees. Please make sure that your cell phones are on vibrate. If you need to take a call, please step out into the hallway before you do that. And with that, I think that I'd like to go ahead and introduce Jean-Philippe. Please.
Thank you, Chris. Hi, everyone. Thank you for is there any crypto people in the room? Crypto people? Is there any blockchain people? Not exactly the same, okay. Who in the room is doing security audit code reviews? Not necessarily crypto, but more generally code audits. Okay, quite a few. All right, so quick introduction about me first. It doesn't work like this. So I've been doing crypto for a while, maybe before it was cool, since maybe 2005, 2006. So back then you said crypto to a girl, she was looking at you, oh yeah. But now you do crypto, you're a cool guy, and it's really nice. So I live in a small country called Switzerland. And I've talked about crypto several times at Black Hat, and always exciting to be here. I'm working for Kuleski Security, so a big company with an HQ in Switzerland and an HQ in Phoenix, Arizona. And I'm also running a small company doing IT security, and I'm doing security at Taurus, which does digital asset, blockchain, custody technology. And I wrote this small book, but you cannot buy it at Black Hat because it's already sold out. But you may buy it at DEF CON if you go to DEF CON. Okay, so we're talking about security audit. So what does it mean in our context? So it's from internet, so it must be the right definition. It says the inspection or examination of something as a building to determine its safety, efficiency, or the like. So we're not talking of audit in the sense, of compliance audit, where you have a checklist and you check point by point, and then either you're compliant or not. So the security audit in our context, it's more an assessment, security assessment of the code. So what do we do concretely? So we, most of the time, have to say we look at the code. Sometimes we look at specifications, documents, at architecture documentation. Sometimes we would have to match one specification against the code, so the customer would give us one specs document, maybe an academic paper or something that they wrote themselves, and they would also give us the code, and we would have to try to match the two and find any discrepancy between the two. But yeah, most of the time, it's finding bugs in code. In code that is doing some crypto functionality. It might be, for example, in the context of blockchain platform, it might be a wallet application. It might be very different stuff. But yeah, the common denominator is that it's using some, let's say, cryptographic components. However, the bugs we find, few of these bugs are cryptographic bugs, but I have to say, if you look at the reports we publish, most of the bugs are not purely crypto bugs. They are software bugs in crypto implementation, but not necessarily purely crypto bugs. Okay. So, of course, we don't do this for free, at least most of the time, so we get paid for it. So a customer would talk to us, say, okay, would you like to review our code? And most of the time we say, yes, of course. Here's the price. And that's it. We publish the report, of course, with the agreement of the customer. So generally, the customer will ask us for the permission to publish the report. So from the perspective of the customer, it's, let's say, a sign of transparency. They want to show that they've been audited. So in very, very few cases, we have the feeling that, they're just interested in having, the publicity and say, we've been audited by these guys in Kuleski. But maybe 90–95% of the time, just from our perspective, people genuinely want to improve their security posture, to fix the bugs, and are really honest about it. So yeah, in many times we publish the reports, and I have to say for blockchain companies, it's more common for blockchain people than non-blockchain people because they tend to be more transparent than other types of companies. So let me just quickly show you how this looks if you've never seen this kind of report. So typically, we would describe the thing we found, the bug or the issue. We would have a small severity score. So here you see it's medium. We're not using CVSS most of the time. So CVSS is a standard specified way of defining severity ratings. But it does not always apply to the thing we do. It doesn't always apply to crypto. So that's why we usually have low, medium, high, or informational severities. So not only we describe the issue we found, the alleged issue we found, but also the recommendation, what we suggest to do, how to fix it, if they want to fix it. And then we send the report, we share the report with the customer, they look at it, they tell us, okay, we acknowledge a vulnerability, we're going to fix it this way. Or sometimes they would just tell us, okay, guys, you're wrong, you misunderstood something. And then we may or may not revise the severity. And after the customer has patched their code, we review the patch and we write the status, okay, it has been fixed this way by doing this, this kind of thing. Okay. So the agenda for today is three main parts. The first one, I will go through a list of common bugs. So I will just show you a piece of code, and just to give you an idea of the kind of bugs we find. And I tried to pick some bugs that are maybe one of the most common, or the most common classes of bugs that we find in real audits. So the names of the customers will be redacted, but these come from real audits. It's not made up. In the second part, I will focus on Rust, on the Rust programming language. So how many of you are writing Rust code? Only? Oh, I'm disappointed. Okay, so you learn about Rust. That's a very nice language. And the last part is maybe, it's less technical. It's about reflecting after these 2 or 3 years what we've learned, what we would recommend for fellow auditors, maybe the errors we've made, what we've learned, what we also recommend for the customers, so what you should ask an auditor when you want your code to be audited, and several ideas that I had when preparing this talk. Okay, a small caveat. So we're not here to make fun of developers. They had a stupid bug, or a bunch of idiots. It's important to remember that it's relatively easy to find bugs, to look at someone else's code and find bugs. But if you've been on the defender side, you know how hard it is to build secure systems. You know how hard it is to write secure code, to write bug-free code. And if you've used the crypto libraries, or if you've written cryptographic primitives yourself, you know how hard it is to get everything right. I myself committed embarrassing bugs, even in crypto. So I know very well how it feels to, when someone points out your mistakes. So the first one, please don't leave the room. This is Haskell, but it's the only Haskell example. It's maybe not the more readable code, but yeah. So I don't know if you can give you maybe 10 seconds to look at this code. You see a passphrase somewhere, and I don't know if you can find the problem in this code. So let me find the laser pointer. It's here. Okay, is there a bigger one? Okay. So if you look at this code, you'll read encrypt chachapoly here. So chachapoly, it's shorthand for Chacha20 Poly 1305. It's an authenticated cipher. It's a way to encrypt data and authenticating data at the same time. So it's a combination of the Chacha20 stream cipher and the Poly 1305 one-time authenticator. So it's calling this function with as first argument this at nonce value and a passphrase and something else, the data that's going to be encrypted. So if you know how chachapoly works, or if you know how any such authenticated cipher works, you know that most of the time it needs as additional input a value called a nonce or an IV. And to be secure, this value needs to be unique for every new message you encrypt. Now if you look up this value, you'll see it defined here, and it's hard-coded in the code to this 0cal4, I don't know where it comes from. But anyway, what will happen is that anytime they encrypt a message, they will use the same nonce. And it's very bad because if you do this, an attacker would be able to decrypt your message. Even though the cipher itself is very safe, But the fact, if you reuse the same nonce, then all your ciphertexts become easy to decrypt, to simplify. So that's something that we found in a major cryptocurrency wallet, very, very famous organization, and it completely defeats the encryption. And of course, they fixed it, but yeah, that's a relatively common type of bug. The second one, so you probably know about the password hashing problem, and also the password key derivation problem. So password key derivation is when the secret is a password, and when you derive a key from this password. So you want to encrypt a message using a cryptographic key, and you get this key from the password, because you cannot use the password directly, it's a variable size input. So typically you would use a hash function, a special type of hash function. So can you guess what's the problem if you do this? If you use the SHA-256 hash function to get a key from a password? Yeah? Okay. Well, the problem, of course, is the password has relatively low entropies, much easier to guess than an encryption key. So a key is, for example, 128 bits, so you have 2 to the power 128 possibilities. In the case of passwords, you have much fewer possibilities. It's much easier to crack a password. If you have like a dictionary, like professional password crackers have, there's a very high chance that your password will be in this dictionary. So, and the hash function SHA-256 is very efficient, which is good most of the time. But if you hash password, you don't want to use a fast hash function. You want to use the hash function as slow as possible to make the password cracking as hard as possible. And that's a very common problem that we've seen in many say, applications. So the right way to do it is not to use SHA-256, but it's to use something like PBKDF2, script, Argon2, bcrypt, where you have not only a password, but also an additional input called the salt. And the point of the salt is to try to simulate a different hash function for every new password you're going to hash. So if you use different hash function for every new password, it means that you have to repeat the cracking effort for every new password that you're trying to break. Okay. This one, I love this one. So in many blockchain projects, so you know how it works. When you issue a transaction, it's like signing a check. So you issue a digital signature. So you sign the check, you sign the transaction saying, I want to send this amount of money to that address, to that guy. And you yourself, you have an address, and typically this address is derived from your key, from your public key. So you have a private key, you go from the private key to the public key, and you go from the public key to the address. So what can go wrong? So you can see it as just hashing the public key, if we abstract this out. Now, if your address is, let's say, 64-bit, can you imagine what can happen? Just give you 10 seconds to think about it, and then I will give you the answer. So you heard about the notion of collision. Collision is when you have different values, different inputs that give the same value when hashed with some hash function. So we've had collisions for MD5, that's why MD5 is not a safe function to use. We've had collisions for SHA-1, that's why SHA-1 is not really nice either. So in this case, there was a very relatively big cryptocurrency in the top 20 at the time, the top 20 in terms of market capitalization. And they were using 64-bit addresses. So it means that you could easily find different keys, different accounts, that would map to the same address. So you have one account, another account, but the two accounts have virtually the same address. They're the same account. What you can also do, if you find someone, if you know someone else's address, then you can compute what we call a pre-image. You can try to find a private key and a public key that give the same address by using this cryptocurrency's hash function. And this will cost, on average, around 2 to the power 63 operations, 2 to the power 63 invocations of the hash function. So in cryptographic, when we talk, when we quantify security, we usually consider that you need at least 128-bit security to be safe today. So 128-bit security means that to break the system, you need of the order of 2 to the power 128 operations. And of course, 2 to the power 64 or 2 to the power 63, it's the square root of this number. It's much easier to break. So to give you just an example, an analogy, the DES cipher that was designed in the 70s, which we don't use today, it has security of 64 bits, well, actually 56 bits, and that's why we don't use it. Otherwise, it's relatively safe. And what happened is that if you could find another key that maps the same address as the victim, then you could steal all the victim's money. You could completely hijack their account. So issue checks on their behalf, and you can even prevent them from having access to their account. So spoiler, the cryptocurrency was LISK, L-I-S-K, and I don't think I've fixed it. Okay. The fourth one, that's a very, very classical one. So you see the penguin. If you know this penguin, you know what this bug is about. So when you encrypt with AES is the block cipher, the standard block cipher, which is very safe in itself. But there are different ways to use it. So when you use a block cipher to process a message of arbitrary size, you need to use what we call an operation mode. So the operation mode is the way you're going to combine your block cipher to encrypt different blocks. And the simplest way is to split the message into a number of blocks and to encrypt each block individually. Now the problem, if you do it, is that if you have two identical blocks, then the ciphertext block, the encrypted block, will be the same. And there's a few other problems, but the upshot is that it's bad. And that's why you can see the penguin if you encrypt the penguin. And we've seen this in, again, an anonymous cryptocurrency wallet that I'm not going to name, but you may guess it. And it's like really a beginner mistake. I mean, if you learn about crypto, you learn this like in the first 20 minutes of your class. And we still find this kind of bug. So what is the solution instead of doing ECB mode? CBC or GCM or something else. And then again, if you use CBC, you are going to use an IV as an additional input, and this IV must be random. And if you use GCM, AES in GCM mode, you need to use a unique IV. Otherwise, it's even worse than ECB. Yeah, so crypto is harder. Another type of bug, so this one was in a hardware wallet. So the form factor was a smart card form factor, and they were using NFC for communications. And we found a bunch of, let's say, shortcomings in this protocol. They were sending the symmetric key in clear. So symmetric key is supposed to be a secret. You don't want to send it in clear most of the time. The pin, however, was not sent in clear, but they were just sending a hash of the pin. So the pin was only 4 or 5 digits between 0 and 9. So it was straightforward to brute force it and guess the pin, even though you only knew the hash. Oh, and by the way, the default pin size was only 3 digits. So relatively fast to brute force. You don't need a GPU for this. And another problem was that the comments were sent without any authentication. So the card was receiving comments from the host, but there was no signature, no evidence that these comments were coming from a trusted machine. So we reported all these issues, and the guys, they fixed everything. But when we've seen this, it was pretty scary. And maybe the last one for this part is, I think we found this one by accident, but I don't know how much of you know the BIP32 standard in blockchain wallets. So it's just a way to derive keys from a seed. So usually you have a seed which is like the master secret, and from this master secret you may derive many different public-private key pairs. So there's a tool called BIP32gen that some people were using, and it would take as an input the seed. So here I give the seed. Where is it? I give the seed as an input. And I want to have the address that corresponds to this seed with M as let's say, the label of the address. And I get this value, 1, J, Z, E, U, O, and so on. Now, if I do the same, but the seed, instead of taking a seed of 64 bytes, I take a seed of 32 bytes only, which is truncated, just truncating the first one. And I observed that I get exactly the same address. I was like, oh shit, what's going on here? So actually what the system was using is accepting any size of input, but silently truncating it to the first 32 bytes without giving you any warning that it will ignore the rest of the input. And I noticed this at the right time. If I hadn't noticed this bug, some people could have lost tons of money. So that's really bad API design. That's really the worst thing you can do. So I submitted a PR and fixed it. But that's really scary if you see that people are using cryptocurrency to store millions of dollars worth of money, and it relies on very, very fragile tools. And if you look just even at very popular Bitcoin or Ethereum code bases, you find many deprecated, many unsafe dependencies, which is pretty scary. Okay, Rust. So Rust is a memory-safe system language. So unlike other memory-safe languages like, for example, I don't know, Go or Java, it doesn't use garbage collector. It's using reference counting, which tends to be more efficient to get rid of memory corruption issues. So we see it more and more use for cryptocurrency applications. I recently learned that one very big cryptocurrency is going to use Rust for their server-side code, which is not unusual, but we see Rust more commonly in client code than in server code. So one example of a cryptocurrency using Rust is Zcash, where a large part of the elliptic curve crypto and pairing is written in Rust. And it's actually very, very, very good code. Okay. So the first thing I do, like maybe in the first 20 minutes, first half hour, when I have to do a Rust audit, is just use the comments from the cargo test suite. So I just try to build the code, see if I can build it, run the unit test. So this can be done using the cargo test command. Then the cargo Clippy is the linter of the Rust language. So you will not find any bugs with Clippy, but the output of Clippy, let's say, gives you an idea of the code hygiene and how careful the developers are. You can also see if they've already run Clippy themselves and if they've fixed anything. So yeah, it's generally if you run Clippy and there's like a ton of issues, maybe it means that the developers have not been very, very careful. Cargo audit is very convenient. So it's checking for known vulnerabilities in the dependencies used by your project. So you can very easily see if there's, let's say, a deprecated dependency or if there's some known problem in one of the dependencies. And maybe the last one is to do a grep for unsafe blocks. So unsafe in the case of Rust. So Rust is generally memory safe, but you can work directly with row pointers, in which case the code is not safe. And this has to be declared inside unsafe blocks. So you write unsafe and you write your code. Let me give you an example. So of course, unsafe means unsafe. It means that you can have classical memory corruption bugs out of bound reads or writes in Rust code, and you may be able to exploit these bugs as you would in C or C++. Okay. And you typically want to do it when you want to use, for example, a C API using FFI calls. So yeah, maybe one of the first easy things we do when we review Rust code. And if you write Rust code, you want to avoid having to use unsafe blocks. There's actually a project by the Rust security community, the Rust security working group, whereby they try to look at many different projects. They look at their unsafe blocks, and they try to find ways to remove the unsafe blocks by writing pure Rust code. Okay. So here's just an example in one wallet application where they would read the seed from one pointer. Here's the seed pointer. And you see that this is called in the read seed function. And this read seed function is called itself in an unsafe block by this wallet from seed function. Okay. So you see, for example, if this pointer is null pointer, then you will get a sig fault or something like this. Okay. Another common bug, so in this case, we're not talking of memory corruption, but of potential panic. So the code will fail without, it will just panic, but without giving you any error message. And typically, you want to avoid this. So in the context of Rust, you can have a panic if you use the unwrap command. So you get an object that is an option or result, but that happens to be none or error instead of an actual object. So typically, you want to avoid using unwrap and use instead the pattern matching feature and do something if you have none or error instead of just crashing. So it's not something that you would exploit to get RC on the program, but that's something that we would report as security issue if we find a panic triggerable by an attacker in some Rust project. Okay. So that's just one example that we found in an audit in some deserialization function. So if you get an error from deserialize, which is here, then where is it? Okay. When you do this unwrap, you would panic if deserialize failed. Okay. So the solution here is for developer to, let's say, to check if there's an error, and if there's an error, do something, write an error message, but not panic. So we see in this case it's not really exploitable in the sense of, RC or memory leak. It's more, what we call DOS, but it's still something that we would report, and we would typically tag it as low severity, depending on the context. It might be medium severity if it's really, really bad, but it's typically not something that we would rate as high severity. So now, if you've done crypto audits or written crypto code, you know that a good practice, good hygiene is to, let's say, remove the sensitive values from the memory, from the stack or the heap memory after using them. So in C, it's relatively easy because you get full control on the memory. You see where each object is stored, and you can overwrite the memory, for example, with zeros or random values. And the goal of this is that if another process is reusing this memory, then you don't want them to read your sensitive values. It might be the keys, the internal state, or the subkeys of a cipher. It might be the plain text. So in C and C++, it's relatively easy to do. We know how to do it safely. But you can't, there's virtually no way to do it reliably in garbage collected languages because the values tend to be, copied everywhere in different places in memory, and you have no control on where these values are copied by the GC. So in Go, Java, or JavaScript, as far as I can tell, there's no way to, remove sensitive values from memory reliably. So Rust is maybe somewhere in the middle. So you can do it. So my understanding, so I'm not a Rust expert. I know a little bit, but I'm not writing Rust full time. So what I've learned is that, from my experience, that it's easier to do it reliably for heap allocated memory than stack allocated memory, because you don't have control on the stack allocator, so you don't necessarily know where your data is stored. And again, internally, your data may be copied in different places, and you can't always, zeroize all the copies of this data. So I've discovered there's a crate, so a package called Zeroize that apparently claims to do this reliably. But again, I don't vouch for it. I don't know how good it is. Maybe if there's Rust people in the room who know better than me, they can give me their opinion on it. There's actually a good, I can show the link later. There's a good blog post about Rasterization that I found somewhere. Okay. Now about Rust and crypto. So what I like in Rust is that most of the time you see code written in Rust, and you realize that on average you tend to deal with better programmers in Rust than, for example, in JavaScript. I mean, no offense to JavaScript people, but to code Rust, you need to have certain discipline, a certain understanding of how memory works. So the code is usually relatively well written, and also the compiler tends to be very, very picky. So it forces you to get a clean code, to get a warningless code. So that's usually pretty good in terms of security. However, there are much fewer tools like static analyzers available for Rust than C. So in C, you have all these analyzers. They're not really useful, but then again, it's nice to run them to get an idea of the code hygiene. But yeah, most of the time, these tools are not really useful when you look for non-trivial bugs. But there's still the risk of timing leaks. So in crypto, oftentimes you want to have what we call time constant code. You want that the execution time of the program does not depend on any secret values. Because otherwise, by simple signal processing, you can measure the execution time and deduce some information on the secrets. So the secrets might be the keys, internal state, the plain text, or anything that you don't want to be public. And when we do an audit, one of the first things we ask to the customer is, what is your threat model? Do you care about timing leaks? They might say yes, they might say no. If they say we don't care about timing leaks, then we try to challenge their entry and try to think if they want to care about timing leaks or not. And well, to be honest, many times they don't have to worry because of the way the program is used. Some other times you really want to have timing protection, for example, in embedded applications. So it's also up to the customer. Maybe they would tell you up front, no, we don't care about time constantness, we just care about performance, and that may be fine. So that's an example we find in some Rust application, in some modulo subtraction operation. And the problem was here, so you had this branching if, and typically when you do this kind of branching, you get a different, let's say, different execution time in terms of clock cycles, because you don't execute the same code and you have a little difference that may or may not be measurable, that may or may not be exploitable, and that may or may not be exploitable remotely. But still, you want to report it because it's not constant time. So that's another example. That's another example in some Rust code in a slightly different project in the ED25519 signature scheme. So in this case, we recommend it to the customer to use constant time. So what we try to do is, we try to put ourselves in the customer's shoes, and most of the time they're not cryptographers. Sometimes they are, but if we can write the code that will be constant time, we try to do it. If it's not, let's say, if it's not too complex, if it's doable, instead of having them write it themselves and sending to us and us reviewing the code. So sometimes it's just more efficient for everyone that we write the patch and then they review it. Okay. So again, I don't know so much about Rust. I love this language, but I'm very poor Rust programmer. Many people know Rust much, much better than me. So this is a very good post by Tony Archeri, who knows Rust really well. And it talks about Rust security and many other aspects of Rust. You may want to check this GitHub organization, Rust Secure Code. They have a repo called WG Working Group, where they try to, you will find this kind of issues where they try to improve the general security of Rust. And I think it's very good resource. Okay. Okay, now for the last non-technical part, what we've learned from this, so I won't show any code here. So maybe the first observation is that, I don't know if you were around 10 or 15 years ago, if you were doing crypto back then, but it's much, much better now for a variety of reasons. People know crypto much better than 10 years ago. There are many more resources, many more books, many more, let's say, accessible books. One of the key driving forces was maybe the revelation of Snowden, of course, because Snowden kind of made crypto cool. Everybody got excited about end-to-end encryption after the Snowden revelations. Another driver is the blockchain, all the blockchain stuff, where you have tons of people with plenty of time of their hands and plenty of money to spend on, doing crypto projects. So from my perspective as a crypto person, it's really cool to see that, people who don't have, let's say, formal education in crypto or security are, let's say, very good at, writing crypto. And I often find developers and often find code where I'm really impressed by people who never really studied crypto, let alone had a PhD, but are very good in terms of both theory and practice. Like, for example, the Zcash team has, people who are, let's say, amazing, who know, cryptographic pairings and who do very complex zero knowledge stuff. And you would never have found this like 10 years ago. Everybody would write, ECB, MD5. So that's really cool. Yeah, like I was saying before, it's we talk about crypto audits, but most of the time we just review code. We try to find bugs. Like if you look at the code and you find like a big mirror corruption, you're not going to discard it by saying, oh, it's not crypto, so let's just ignore this bug. So we report any issue that we can find, and most of the time the issues we find are not purely crypto bugs. They may happen to be in the crypto, but not pure crypto. So for this, you need to know, you need to have some knowledge of the language. And it's not always easy because you cannot be an expert in every single language on Earth. So we have been reviewing code in Java, JavaScript, C, C++, Python, Rust, Go, even Haskell. So you can be an expert in all of these languages, but you need to be comfortable enough, to deliver good quality for your customers. Or you need to find one person in your organization who can help with the language knowledge. Okay. So when you start an audit, to get the best value from the work, both sides must be prepared. So as an auditor, when you will do the work, so of course you must have some degree of familiarity with the thing you're going to audit. For example, if they ask you to review, I don't know, some zero-knowledge proof, then you should know what zero-knowledge proof is about. You should know this kind of zero-knowledge proof, and you're not going to charge the customer for learning about this type of zero-knowledge proof. You will charge the time for, learning their own specific version, but not for general knowledge. Likewise, if they ask you to review, I don't know, Haskell code, then you're not going to charge time for learning Haskell in 1 weekend. You need people who have already been working with this language for a reasonable amount of time and who are already comfortable doing audits for this type of language. Now, on the customer side, so oftentimes people would come to us and say, oh, please review our code. I say, okay, well, what do you need exactly? What do you want? Or just find any security issues. But then we ask them, okay, what is your threat model? What are the critical components in your system? What are your, let's say, critical assets? Have you already hired people to do security audits? Have you used some automated tools? Do you have an internal, security SDLC process? So it's very helpful from an auditor perspective when the customer comes with a precise list of, let's say, what are the main threats? What are the main assets? What are the parts of the code that make them nervous? So where do they expect us to spend most of our time? So it might take time to do it, but you will get a much better value from the audit if you take maybe a few hours, a few days to do it properly. Okay. And of course, documentation is cool. In some cases, there's no documentation. People will just give you some source code, sometimes without any comment, and then you have to kind of reverse engineer the logic of the code. And it's not the ideal situation, of course. So when you start an audit, you also have to estimate, how much time it will take, how much it will cost for the customer, and it's not always easy. So a simple way to do it is just to count the lines. So you can use the clock tool, and you can get a ballpark estimate by just counting the lines of code and saying, okay, in our experience, it takes maybe 3 hours per 200 lines of code or something like this. I don't have the figures in mind. So it can give you, let's say, a rough ballpark estimate, but it also depends a lot on the complexity of the code, on the language, on the complexity of the project, on the amount of, let's say, previous knowledge. And it's also hard, let's say, sometimes to put a price tag. So one way to do it, of course, is to charge a daily rate, a flexible daily rate. In some other cases, it might be better to charge a flat fee. Say that you will pay this amount regardless of the time we spend. And so if you've been in this situation, you know that it's not easy to do, but you want to do something that is fair for everyone and is flexible enough. Because it might take you more time than expected, as well as it might take you less time. So you want to be able to deal with this situation in a way that is fair for everyone. So when do you find the bugs? So I think there are two extreme cases. If you've been auditing code, maybe this will sound familiar to you. So in some contexts, when the code is relatively simple, when you're very familiar with the type of project, for example, a wallet, in our cases, you would find maybe 80% of the bugs in the first 20% of the time, or even less. So you would find all the low-hanging fruits, and then you're getting diminishing returns. So you may spend a lot more time and maybe find nothing, or find non-trivial bugs. So you always want to spend more time and look for non-trivial bugs. But sometimes you just found nothing, and it's frustrating. But yeah, sometimes there's just nothing to be found. In other types of project, the most complex ones, for example, when we audited Zcash, you may have very, let's say, steep learning curve, and it might take you several days to get familiar with the code base and understand what the code is doing, understand the whole logic, and you won't find any issue or maybe some small problems in the code. But in this case, you will start finding bugs or logic bugs or design bugs after maybe several days or maybe even after 1 week of review. So it also depends on the complexity of the code, on, let's say, the previous knowledge of the auditors and the documentation from the customer. So, severity ratings. So that's an important topic. I was discussing it yesterday with another auditor company. So you may, like I mentioned before, you may want to use CVSS, but then again, CVSS is not always the best tool for crypto audits. So what's important from my perspective is to consider the exploitability and the impact. It's very well-known stuff in security. So you don't, let's say, you don't put high severity rating just because it looks bad, because you think it's stupid. You really have to consider how exploitable it is, and what's the impact. And I think maybe there's also like psychological bias, whereby auditors maybe tend to overestimate the severity. We've also sometimes underestimated the severity, but I think any auditor knows this problem that you always want to have a high severity vulnerability in your report, but you have to think very carefully about the actual risk and do something that is fair for everyone. And what's really important is to be consistent across the report and consistent across different engagements. So if you write one kind of bug high severity for one customer and the same bug medium severity for the other one, then it makes no sense and people will tell you that it's unfair because it will be unfair. So in the context of crypto, if you see people using ECB, you might scream and say, oh, that's completely stupid, that's high severity, you should never do it. But then you have to think about what's the actual risk for the customer, how exploitable it is, and it might end up being a very low severity or even no severity bug in some cases. Yet it should be fixed, but it's not because it looks stupid that it's bad. And again, you consider the security model. So, for example, we have audited a proof of work. So proof of work is a kind of big, slow hash function. And here the thread model is pretty unique. The goal of the attacker is to compute the output faster than expected. So it's not about pre-images or collision. So of course you want the hash function to be collision-free. But the main goal here is to make the function impossible to replicate or impossible to compute in a way that is significantly faster than expected by the designers. So yes, that's one example among many others, but you always have to think, what is the program doing? Who are the attackers? What is the attack surface? And what's the risk from the customer's perspective? And you always biased because we all have our own experience. We tend to see things from our own perspective, and I've been in several situations where I was tempted to put, for example, a given severity, and then I tried really to think about what's the actual risk for the customer, and then sometimes it made me change and revise the severity level. So generally, like I said at the beginning of this talk, you really have to be very understanding with the developers. Don't make them feel like they're idiots or did something stupid. We all write embarrassing code. And when you write the report, it's really important, to turn it to write in a way that is positive. Say, okay, it's not the best practice. You should do it this way, not say something really offensive like, oh, that's really bad or stupid. I think it's really important. If you have been audited, you know how it can feel if something writes a report in a tone that is not very adequate. And you should write the description in a way that can be understood by your target audience. So typically the audience will be developers. So you want to use a language that is understandable by the developers. Sometimes you have to write a report also for the management, so you would write a high-level executive summary. But when you write reports, we mostly think about the guys who are writing the code, and we will have to fix their code. And try to help them as much as you can. So for example, if you give recommendations, maybe try to give links to actual standards or actual documents or websites that help them how to find a mitigation. Maybe you don't know the best mitigation. Maybe they know better the code than you do most of the time. But you want to give them as much help as you can. And after they've patched it, you review the patch, and you tell them if you think it's good or not. So I think it's important to keep communication ongoing with customers as you walk through the audit. One way to do it is just to get the code, work in a bunker for 2 weeks, and then share the results. But we found it way more efficient, for example, to have a Slack channel with the developers and ask as many questions as we can. For example, if we're not sure about something, if we don't understand some piece of the code, it just might be more efficient to ask the developer rather than spending half a day trying to figure out what's going on. And sometimes we would misunderstand, we'd overestimate or underestimate a problem. So we would just ask the guys directly, okay, what do you think about this bug we found? And they would tell us directly, oh, right, that's a problem, we should fix it. And this will also save you time, because if you misunderstood some part and if it's not a bug, and they tell you it upfront, then you won't have to write down the report. Okay. And what's also important is if you deal with a system that's already in production, it's much better to report critical bugs as you find them instead of waiting for the final release of the report. And so last but not least, of course, when reports are published, it's sometimes embarrassing to see people commenting on Reddit or other places and saying, oh, but look, it's been audited, so it's safe. So we always try to say, we only have so much time, we only have so much capabilities, we will not find all the bugs. When you hire different companies to audit the same piece of code, different companies, they will find different bugs most of the time. So security audits, like I said, they tend to be broader than they are deep. You are limited in time, you are limited in budget. and limited in scope. Sometimes they would just tell you to review this part of the code and only the code that they wrote and not the dependencies. So what we do sometimes is just check for any known vulnerabilities in the dependencies, and if there's any critical dependency, then we might ask the customer if they want us to spend time reviewing this specific dependency, because we think it makes sense from a risk perspective. But we'll never review all the dependencies, of course, especially if we look at JavaScript code. So, and the bugs can also be, of course, in the runtime of the language or in the OS in the platform. So it's not only the risk is not only in the code written by the customer. Okay, so I have 5 minutes left for questions. I will be happy to take questions here or after my talk. Thank you for listening. I hope it was useful to you, and feel free to reach me by Twitter, email, any channel. Thank you very much.